Okay, so I wanted to come up with a rather simple research question to follow and to collect data on that would not defy the FERPA regulations. So I didn't want to do anything related to your grade or performance in the class. The research question is there a difference by gender in the number of Google results produced? In other words, if you go to Google, type in some kind of search, let me type in mine here. So I'm going to google.com, typing in Daniel Showalter, and I'm getting 6,110 results. I also get my baby picture there conveniently. So what I'm doing here is just going to collect the number of Google hits on each person in our class. So the first question is our class a representative sample of all females and all males? Absolutely not. This is purely for convenience sake. This is a convenience sample, and this would cause major problems in generalizing the results of this study to all females and all males, like we'll talk about later in this week's lesson. But for now, let's look at the procedure of this statistical test here. So I get the question, is there a difference by gender in the number of Google results produced? And I come up with a research hypothesis. I'm thinking, okay, well, maybe there's more search interest in females, so I'm going to say that females have a higher average number of Google search results than males. And again, I'm saying average. So if I were to take all the females in the world, Google all of their names, average all those numbers, and then do the same with all the males in the world, I'm suggesting here that the average female number would be higher. Now, typically you would want your research hypothesis based on some research literature, studies, previous, or some good reason for the hunch. Certainly if you have what I have here, which is called a one-tailed hypothesis, I'm specifically guessing that one group is higher. Now, if I didn't know at all, what I would typically do is say there is a difference by gender, but I'm not sure which way it is. In either case, whether I say that females are higher, males are higher, or just that there is some difference, but I'm not sure which direction it's in either case, my null hypothesis will be that there is no difference. So null means nothing, nothing going on, no difference between the 2 or 3 or however many groups you have in terms of their averages. And this is really what underlies the statistics here. This null hypothesis is what we really get to examine when we do these statistical tests, even though the research hypothesis is what we're more interested in. So based on what we decide about the null hypothesis, we make claims about the research hypothesis. Okay, all of that to say, let's dive in here and see whether males or females, at least as represented by our class, have more Google hits. So I went through each of these. I'll show you. Let's not do it that way. Let me highlight. Okay, so here you can see the numbers. Turns out that Roz is not a very frequent name, whereas Ryan Thomas had over 500,000, and Jing came pretty close to that. Jing Wu. I actually used first and last names here. Don't worry, I didn't look at anything beyond that. I'm much too busy to do that. But these are the results here. And we could easily find a mean. In fact, let me just grab these. Okay, I go to the bottom right. I get the mean is 1,170 for the girls. And for the boys, our mean is 125,000. So boys are clearly being pulled up by Ryan and Jing here in terms of numbers of hits. And seems like we could stop right there because we had 125,000 hits on average for the boys and a little over 1,000 for the girls. So clearly there's a major difference. This research hypothesis is completely wrong. Males have a much higher average number of Google search results, right? Wrong. So here's the delicate balance between sample and population. Within our sample, yes, within our sample, the males had many, many, many more hits on average than the females did. But we're not really concerned about the sample, we're concerned about the population. So this is why we do an inferential statistics test. And to do that here, we could do some of these with the built-in functions, but let's get an add-on and let's just get this XL minor analysis pack. Okay. So we're going to get that. We're going to accept these terms, and then if we go to add-ons and click on this start, we'll get the tool pack over here. The tool pack will let us do all kinds of different statistical tests. We're concerned with t-tests. Now we have three options here. Paired to samples. What that means is each female in the class would be paired with a male in the class. Clearly that's not the case. We have 6 females, 8 males. Beyond that, we have no clear way of pairing the males and the females. If this was a marital statistics class and you had to sign up as a couple, then we would potentially be able to pair you, or there may be other ways of pairing if we had equal amounts within each group, but we clearly don't in this case. So that leaves us two different options here, equal variances or assuming unequal variances. We don't really have any good reason to assume equal variances, so I'm going to assume that the variances, what is this variance? This is the variance of the number of hits for all females and the variance for the number of hits for all males. Are those two variances the same? I have no reason to assume they are, so I'm going to go with the unequal variances. I'm going to start off by selecting the number of Google hits for females and click in there on the variable 1 range. Then I'm going to select for the variable 2, click on the range. I don't know why that order of clicking seems to work out for this, but feel free to type in these cell values if you need to. Hypothesized mean difference. This is talking about the null hypothesis. So the null hypothesis was that there wasn't any difference. In other words, that the difference was 0. We don't want labels. Let's leave our significance level at 0.05. This is a 5% chance of making a type 1 error. That's what we're willing to take. And then output range, there's going to be a bunch of output, so I'm going to choose the top left corner of that output. D6 looks nice here because it'll fit into the sheet without overlapping any of the current data. So I'm going to type in D6 there, and we'll output that. Okay, so first we're given the means. We do need to figure out which is which. We've already figured that out by looking. This is the females, this is the males. I may even type that up there just to keep myself straight. And you can see the variance here. It's high for the females. It's absolutely enormous for the males because we had, again, Ryan and Jing much, much higher than the others. Number of observations. And we get down here to what's called this T statistic. So this is essentially saying the number of standard errors away from the mean of 0. In other words, the females here were 1.51 standard errors below the mean for the males. Now the question is that significant? So we look at that in two ways. The two ways should match up. It's kind of a way to check our answer. The first is the p-value. We're dealing with we did a one-tail test because we were looking at, do females have a higher average number? Now technically we guessed the wrong direction. As soon as we see that the male mean was actually higher than the female mean, we would reject this null hypothesis. So in general though, we're going to guess in the right direction. It's just a matter of whether the guess was significant or not. In order for it to be significant, this one-tailed p-value, because we had a one-tailed hypothesis, should be less than our significance level. Now, what was our significance level? Remember over there we set it at 0.05. So our p-value here is 0.08, which is not less than 0.05, which means we fail to reject the null hypothesis. We fail to reject it. In other words, we were not able to come up with any convincing evidence in favor of this research hypothesis. It does not mean that we found that males and females are equal. In other words, that there is no difference. It doesn't mean that just because we didn't get below that 0.05 alpha level. But what it does mean is we were not able to come up with evidence in support of our research hypothesis. Okay, we can also double check that, because this t-statistics, this 1.51 standard errors below the mean, what we'll first do is take the absolute value of that. So what we want to say is 1.51 standard errors away from the mean. In either direction, it doesn't matter. What we need to see is, are we going to be far enough away based on what this rejection region would be? We would have to be higher than the critical value for the type of test that we're using. We're doing a one-tailed test here, and the critical value is 1.89. In other words, in order to show a significant difference, we need to be at least 1.89 standard errors away from the mean. In our case, we were not. We were 1.51, which means, again, we would fail to reject the null hypothesis. So whether we're looking at whether the p-value is less than the alpha value, or whether the absolute value of the t-statistic is greater than the critical value, both of those should give us the same result. Either both should point towards rejecting the null hypothesis, or both should point towards failing to reject, which in our case we did. So in simple terms, again, we would say that our study did not provide any evidence to suggest that females have a higher number of average Google search results. If our research hypothesis had simply been there is a difference by gender, but we don't know in which direction, that would have been a two-tailed test. We would have used these values here instead, and in that case, we still wouldn't have rejected. Our p-value would have been higher than our alpha. Our t-statistic, the number of standard errors away from the mean, certainly would not have been high enough to reach this critical value, and we still would have failed to reject. There are times where the one-tailed test might be able to reject, even though the two-tailed test would not. But this is not something you look at in retrospect. This is something that's decided all the way at the beginning when you set up your hypotheses before you even collect the data. You should know whether or not you're doing a one-tail test or a two-tail test. You should also know what your alpha level is at this point. Think about it. If you were able to first look at your p-value from your data and then set your alpha level, you could clearly determine whether or not you would reject or fail to reject the hypothesis, and it would be kind of cheating, which is why before we ever conduct the test or collect the data, we set that alpha range there.